All right, a restaurant server shoves a ketchup bottle with a mass 0.45 kilograms to the right along a smooth, level counter. The bottle leaves their hand, moving at 2 meters per second, then slows down, and as it slides because of a constant horizontal friction force exerted on it by the countertop. It slides for 1 meter before coming to rest. What are the magnitude and direction of the friction force acting on the bottle? So the first thing we want to do is draw a picture. So I'll just draw the ketchup bottle as simply as I can, where it starts and where it ends. And let's indicate we have an axis here. And we might as well call that the x-axis. So we have a picture, and we have an initial position and a final position that we can call 0, and we'll just call that x. We know that this is 1 meter. We know that the initial velocity of the bottle, v0, is 2.0 meters per second. We know that it ends with a velocity of 0, and we also know the mass, and that's indicated here. And so that's probably a good enough picture to start. We have a picture, good. The next thing we want to do is write down what are our knowns and what are our wants. So we have a picture, we want the knowns and wants. So we see them listed there. The mass, 0.45 kilograms. We know the initial speed, v0, 2.0 meters per second. We know the final speed is 0. We don't know the time it takes. What else do we not know? We don't know the acceleration. We want the frictional force. So this is what we want. That's what we're going for, and I can see what kind of information we're given. I guess suppose we're also given that x0 is equal to 0 and the final x is equal to 1 meter. So we want the force, and we're given information about position and velocity. So in terms of the concepts that might be relevant, things that might be relevant are the physics of motion, in other words, kinematics. And we might also need to use the physics of forces, net forces, and of course, Newton's laws. So there are some equations that go along with those concepts. Let's go ahead and write them down. The equations, we have an equation that looks like x equal to x0 plus v0, t plus dot, dot, dot. We have v is equal to v0 plus dot, 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 and we have v squared. And I'm only going to write this one down in full because I can see that actually those top two equations, 1 and 2, would require time, and we don't have time, we don't need time. Anyway, those are the relevant equations for kinematics, and we also have Newton's laws. In other words, net force is equal to mass times acceleration, which I will write this as the net force just in the x direction is equal to mass times the acceleration in the x direction. We only have motion in one dimension. And that should be, those 4 equations should be enough to get us to the end here. What we notice is that in order to figure out anything to do with force, which we want, something contained in the net force, we apparently are going to need something, we're going to need to know what the acceleration is. And so that is what tells us that we want to start with kinematics. So let's go ahead and switch colors and now just begin to start our numerical analysis. Let's switch this to dark red. We can solve for the acceleration most easily using equation 3. So here's where we are going to try to solve this. So using equation 3, we can rearrange that equation to solve for the acceleration, realizing that the initial velocity is given, the final velocity is 0 to a delta x. And so using a little bit of algebra, we could solve for the acceleration. In fact, let's just use this equation completely, write it this way, v squared minus v0 squared over 2 delta x. That will give us the acceleration. What is that? 0 minus 2 meters per second squared divided by 2. The change in position is 1 meter. That gives us the acceleration, which is minus 2 meters per second squared. Okay? Now that we have the acceleration, it's the acceleration in the x direction, we can insert that into Newton's second law, in other words, equation 4, and we'll be able to figure out what the frictional force is. Now, what I haven't drawn yet, though, is a free body diagram for this scenario. So let's do that in a different color. The free body diagram that will help me to figure out what the net force is looks something like this. This dot represents the ketchup bottle. We know that there is a gravitational force and a normal force acting on the bottle, but we don't really need that information. We know that those are going to cancel because the motion is only horizontal. There is a frictional force which points this way. I'll call it F with a subscript F. So using Newton's second law, which is equation 4, we can put in what our net force is, which is the frictional force with a minus sign. That's how we account for the fact that it points to the left. That's equal to the mass times the acceleration in the x direction. Now we can plug in our values and figure out what we have. Minus the frictional force is equal to the mass of the bottle times the acceleration of minus 2 meters per second squared. There are two minus signs, they cancel, and what you learn is that the frictional force has to be 0.90 and the units are newtons.